Okay, so our next speaker is Marge from the University of Cambridge, so a local speaker, and he probably has the longest title. He's going to talk about integrated offshore wind farm design, optimizing micrositing and cable layout simultaneously. Thank you very much.
So basically what I'm going to talk about very briefly is the role that intermittence plays in wind farm design as to whether or not a given wind farm should actually be constructed. So, as we know, at any given point in time, even if you know the turbine layout, even if you know the incoming wind speed and you know the incoming wind direction, it's still incredibly difficult to know what the power output of the wind farm is going to be. However, Jensen's model has been okay at creating on-aggregate wind power output scenarios for a given turbine configuration across different wind speed inputs, across different wind direction inputs. One of the problems, though, is that Jensen's model is often currently not used in conjunction with the true optimal electrical configuration of the layout. So for instance, very simplistically, if you expand a layout, true, you might be producing more power from the individual turbines, but you might not be capturing the true cost to run more expensive, longer, thicker cables between the turbines. So what my team did is we proposed a new design process for adequately financially modeling what a wind farm would actually produce over the financial life of the plant by first taking proposed turbine layout schemes, either traditional turbine layout schemes or heuristically proposed turbine layout schemes, perturbing each of those turbine layout schemes, expanding, contracting, rotating those schemes, optimizing each of those individual schemes, and based on the optimized individual schemes, then adequately being able to compare across economic scenarios which of those turbine layout schemes are most robust. And our model itself was incredibly robust. It could do just about everything except for, on its own, propose new non-standard turbine placement schemes. As it turns out, even implementation of standardized turbine schemes is oftentimes not optimal. As soon as you start considering things like the electrical layout and the cost of land associated with the individual schemes. One of the most powerful aspects of a result is even though our model was only able to consider finitely many perturbations of each turbine layout scheme that we were considering, we were able to create these powerful economic curves to represent the objective function so that we could run different economic scenarios on a given layout scheme after only finitely many runs of the actual individual turbine layout scheme being considered. And finally, we were able to show up to 5% financial viability increase for the wind farm, making it more likely that even if you're only considering standardized turbine layout schemes, that the farm in the first place should be built offshore. Okay, thank you.